What if I told you that there's a question in computer science so profound that its answer could revolutionize fields like cryptography, logistics, and optimization? Welcome to the intriguing world of P versus NP, an unsolved question that has left the brightest minds in computer science and mathematics scratching their heads for over half a century. At the heart of this enigma lies the concept of problems and solutions. In computer science, we often talk about problems that a computer can solve and solutions that it can verify. We classify these problems into two categories, P and NP. P represents problems that a computer can solve quickly, while NP represents problems for which a computer can verify a solution quickly once it's found. But here's the conundrum. Can every problem that a computer can verify quickly also be solved quickly? This is the essence of the P versus NP problem. If P equals NP, it implies that hard problems like factoring large numbers, or the infamous traveling salesman problem, are not as hard as we think. They can be solved efficiently, revolutionizing fields from cryptography to logistics. On the other hand, if P does not equal NP, it would mean that some problems are inherently difficult to solve, even if their solutions are easy to verify. This would put a bound on what we can compute efficiently, highlighting the inherent limitations of computation. First formulated by Stephen Cook in 1971, this question has remained unresolved, despite decades of research. It's so significant that the Clay Mathematics Institute has even offered a substantial monetary prize for its solution, as part of their Millennium Prize problems. The P versus NP problem is more than a technical question about algorithms. It's a deep mystery about the nature of computation and the limits of what we can solve. It's a question that represents our persistent quest to understand the inherent possibilities and boundaries of algorithms. This is the P versus NP problem, a question that stands at the heart of computer science and mathematics. Before we delve deeper into the P versus NP problem, it's essential to understand what P and NP mean. Imagine you're in a maze. If you're lucky or clever, you might find the exit quickly. This scenario represents problems in the class P, where P stands for polynomial time. These are problems that a computer can solve quickly, or more technically, in polynomial time. This doesn't necessarily mean the problems are easy, but that they're within the realm of what a computer can handle efficiently. Now picture a different scenario. You're not in the maze this time, instead you're hovering above it, looking down. Someone hands you a suggested path through the maze. You can easily trace the path with your finger and verify if it leads to the exit. This represents problems in the class NP, which stands for non-deterministic polynomial time. These are problems for which a solution, once found or given, can be quickly verified. The classes P and NP are central to the question of the P versus NP problem. You see, all problems in P are also in NP. If you can quickly find a solution, you can certainly quickly verify it. But the big question is whether the reverse is also true. Is every problem that can be quickly verified, every problem in NP, also one that can be quickly solved, a problem in P? This question is the crux of the P versus NP problem. It's like asking, if I can easily check a solution to a problem, does that mean I can also easily find the solution in the first place? If the answer is yes, then P equals NP, but if the answer is no, then P does not equal NP, and there are some problems for which finding a solution is inherently harder than checking it. The question at the heart of the P versus NP problem is whether every problem whose solution can be quickly verified by a computer can also be quickly solved by a computer. So, what would it mean if P were equal to NP, or if they were not equal? Let's delve into the implications of this enigmatic question. If P equals NP, it would mean that every problem whose solution can be quickly verified by a computer can also be quickly solved by it. This would be a groundbreaking revelation. The complex problems we currently consider to be time-consuming and difficult to solve, like the traveling salesman problem or the factoring of large numbers, could be cracked efficiently. The implications of this are immense. Just imagine the revolution it would bring in fields like cryptography. The security of most modern encryption systems relies on the fact that certain problems are hard to solve. If P equals NP, these encryption systems could be broken easily, necessitating the creation of new cryptographic techniques. In logistics and optimization, solutions to problems like route planning and scheduling, which often take considerable time and resources, could be found much more efficiently. This could drastically improve operational efficiency in numerous industries around the world. On the other hand, if P is not equal to NP, it would mean that there are certain problems for which finding a solution is inherently more difficult than verifying it. This would confirm that there are fundamental limitations to what computers can accomplish efficiently. It would mean that despite our technological advancements, there are problems that we can't hope to solve quickly. This could lead to a renewed focus on developing heuristics and approximation algorithms, methods that provide good enough, if not perfect, solutions to complex problems. So, whether P equals NP or not, the answer will have profound implications. If P equals NP, we face a revolution in problem solving. If P does not equal NP, we face the reality of computational limitations. Either way, our understanding of computation and its potential is fundamentally changed. Therefore, the P versus NP question has far-reaching implications for our understanding of computation and its limits. The P versus NP problem has been a central question in computer science since it was first formulated by Stephen Cook in 1971. The stage for this profound enigma was set over 50 years ago. Cook, a computer scientist, introduced the world to this conundrum while proving that the Boolean satisfiability problem, or SAT as it's commonly known, is NP-complete. But what does that mean? Well, NP-complete problems are a special class of problems. They're essentially as tough as the hardest problems in NP. If you can find a polynomial time algorithm for any NP-complete problem, it implies a similar algorithm for all problems in NP. It's like finding a golden key that opens all the doors in a grand castle of complexities. Cook's groundbreaking work laid the foundation for our understanding of computational complexity. It gave us a way to classify problems based on their difficulty and the resources required to solve them. And most importantly, it gave us the P versus NP problem, a question that, to this day, continues to baffle the greatest minds in computer science and mathematics. The Clay Mathematics Institute, an organization dedicated to supporting and recognizing excellence in mathematics, acknowledges the significance of this problem. They've included the P versus NP problem in their Millennium Prize problems. These are 7 problems, each carrying a bounty of $1 million for anyone who can crack them. The P versus NP problem is in this illustrious company, a testament to its importance and complexity. But despite the allure of the $1 million prize and the promise of eternal glory, the solution to the P versus NP problem remains elusive. It has been over 5 decades since Cook first posed the question, and despite countless efforts and numerous attempts, we are no closer to an answer. Despite decades of research, the P versus NP problem remains unresolved, a testament to its complexity and depth. The quest to solve this problem continues, reflecting our enduring fascination with the mysteries of computation and the inherent limits and possibilities of algorithms. It's a challenge that remains at the forefront of computer science and mathematics, a puzzle waiting for its master solver. So, where does that leave us in the quest to solve the P versus NP problem? Well, in the simplest of terms, the quest continues. Despite the passing of more than 5 decades since its inception, this enigma remains one of the most captivating unsolved problems in computer science and mathematics. It's like a mountain peak, shrouded in clouds, tantalizingly out of reach yet ever compelling. Our brightest minds, armed with the tools of computational theory, cryptography, and optimization, continue their relentless pursuit. They are driven by the tantalizing possibility of making a breakthrough that could redefine the boundaries of computation. Each attempt, each hypothesis, each proof, whether it succeeds or fails, contributes to our growing understanding of the inherent complexities of algorithms in computation. The P versus NP problem is more than just an abstract theoretical question. It's a beacon, guiding our exploration into the heart of computation. It prompts us to ask, what can we compute? How fast can we do it? Are there problems that are inherently difficult to solve, no matter how advanced our computational machines become? These questions are crucial as we continue to push the boundaries of technology and strive for breakthroughs that could change the world. This problem also embodies the beauty and the challenge of scientific inquiry. It illustrates how a seemingly simple question can open up a world of complexities and how the pursuit of a solution can lead to profound insights. It's a reminder that the journey towards understanding can be just as important as the destination itself. So, the quest continues. Researchers around the globe are tirelessly working, hypothesizing, testing, and learning. They are driven by curiosity, by the challenge, and by the potential impact of their work. And, who knows, one day, a solution may emerge shedding light on this profound question and possibly transforming our understanding of computation. The P versus NP problem, a seemingly simple question with profound implications, continues to challenge and inspire the brightest minds in computer science and mathematics. And as long as this problem remains unsolved, the quest, the exploration, the journey towards understanding will continue to unfold.